I will talk about something that was talked about before already, namely the interpretation of quantum theory. Now, before there were basically 2 points of view that were being promoted. I'm trying to give a little bit of an overview and maybe put it into context to a certain extent. Let's briefly talk about quantum theory, why we bother talking about it, and what it is. I'll give you some rough idea. So it's certainly the most successful theory in the history of physics. That's what I want to say, and that was mentioned already. It's precise to 10 decimals, or maybe 11 now. It covers everything from subnuclear particles, atoms, molecules, everyday objects, stars, galaxies, and the universe. It explains lots of things, the stability of atoms, the stability of tables, and also the stability of the genome, something that was stressed by Schrödinger. We'll come back to him. It forms the basis of modern microelectronics, in particular cell phones, computers. All our modern technology would not exist without quantum mechanics. So, what is it? Before quantum theory, I call it quantum theory, it's a little more general. Before quantum theory, there was the classical theory of physics, and a typical example, I mean, the example, was really the mechanics of the heavens. So this is supposed to be the solar system, supposed to give you some rough idea of the solar system. And this solar system was understood by Isaac Newton, and it was like a clockwork. It was called Newton's clock, because it has the feature, if you know the present state of the solar system, that means if you know where every body here, every planet is at the moment, and its velocity, if you know those data, you can predict everything in the future. And equally well, you can predict the past, because the past is really like the future. In the classical theory, there's no difference, really. It's a very mechanical worldview, and it has been superseded by quantum theory. Now, the state, I said the classical state is just all objects, you know where they are, and you know in which direction, how fast they move. A quantum state is something totally different. A quantum state is often called the wave function, denoted by this nice letter, psi. It doesn't describe facts, like something is sitting somewhere and moving at a certain speed. It does describe possibilities and the probabilities for certain possibilities to be realized. In particular, particles do not have precise locations or velocities. It is not a deterministic theory. That means the future is not fully determined by the past. The present does not determine the future, and there's a fundamental difference between past and future. The past consists of facts, documents, records, things that can be read about the past, you know, history. It's there. It cannot be changed. The future consists of possibilities. There's a very strong difference and asymmetry between past and future. So the basic problem, to come to that, and that's the problem about which the whole debate or battle of the interpretation rages. The basic problem is, how are facts created? From this wave function quantum state that describes only possibilities, potentialities. Well, it's understood to a good extent that certainly the interaction with the environment is the essential point. So one example which everybody may know, if you have some radioactive substance, you know, a radioactive atom decays and you have some kind of counter, some detector as it's called, it will click. So that means there's a certain fact created in a certain place and at a certain time. This we would like to call events. The event, to say it again, the event means just creation of a fact at a certain place at a certain time. It's not a point, but it's localized in space and time. So the point of quantum theory is that the events are not really predictable, only their probabilities, the probabilities that certain facts are being created. So far, I think there's consensus. The consensus goes away when we ask, is this all we can say? So, now let's go back to the history and the main battle line. There's an orthodox camp. If I roughly group the interpretation into two groups, there's the orthodoxy and the heresy. And the leading figures of the orthodoxy, of the orthodox camp, was certainly Niels Bohr, and then many people after him. I'll come to that. And interestingly, the heretic camp that said this quantum theory was not complete, there was something essential missing, was led by Albert Einstein, 2 Nobel Prize winners in 2 consecutive years. So that tells you already that's not so obvious. I mean, if the most famous physicist of the 20th century belonged to the heretic camp, and he was not only the most famous physicist, he was also one of the most important pioneers of quantum theory. But he didn't believe the orthodoxy. He wasn't happy with it. But let's first talk about the orthodoxy. The first crucial thing, and that's an insight that is not denied by anybody, it's the so-called ensemble interpretation. What does that mean? It means that the quantum state does not really refer to an individual object or system, but it describes an ensemble, a collection of identically prepared systems. And it really contains all our knowledge of the system. In that sense, it's not enough to predict the future, but it's all we can know. So this was proposed by Max Born in 1926, also got the Nobel Prize much later for that. Basically, you can say that's the don't ask, don't tell prescription about the interpretation. You stop here and you can do physics, but you may not be happy. It's enough for the practitioner, but maybe not for a philosophically minded person. And that's why the battle rages on. But let's continue with the orthodoxy that was worked out in more detail in Copenhagen. That's why it's called the Copenhagen interpretation. It's a dual description. We heard about the importance of duality. It was really worked out by Niels Bohr and not his student, but his postdoc, we would say nowadays, Werner Heisenberg, who was one of the creators of quantum mechanics as we know it. And the dual description means you look at one part of the world, namely the microscopic part, you call that the quantum world, and then you make a cut. And the macroscopic world is the classical world. And on one side, you have potentialities, possibilities. On the other side, you have facts. And I drew a little arrow going from the potentialities to the facts. This arrow was later called the collapse of the wave function. And obviously, or as I said, it's induced by the environment. Or more precisely, people said it's induced by observation. Now, I put in a more modern word, decoherence, but that's how it's understood nowadays in more detail. But let's leave it at that. So the orthodox interpretation was pushed further. I said there's this cut between the quantum and the classical world. Well, where exactly is it? Now, Copenhagen people, Bohr and Heisenberg, they argued already, and they convinced people that you don't have to locate it precisely. You can, for instance, include part of your measurement apparatus or all of it on the quantum side, because after all, it's also made of atoms, molecules, and so on. Now, Eugene Wigner, Nobel Prize winner, 1963, he pushed it further. He said, well, the cut should be really in the brain. So he thought about the following. He has a friend who goes to the lab, makes a certain measurement, and in his view, the wave function, the fact is created only the moment his friend tells him, and his brain, his consciousness, registers this fact. That's pushing it to an extreme. Now, why were many people were not really fully happy with this orthodox interpretation? And why was that? It's because they are paradoxes. So one of the pioneers of quantum mechanics was Schrödinger. And in 1936, he invented this thought experiment of the Schrödinger cat. We heard about it already. But he introduced it with the words, one can even set up quite ridiculous cases. He thought it was too extreme. Nobody believes that there is such a thing as a superposition. Well, what does that mean? As a cat that's at the same time dead and alive, or awake and asleep. No, maybe that's easier. He said the superposition of a dead and alive state of a cat, could that really be true, that its fate is defined by observation? When you observe it, then all of a sudden it jumps. It's either dead or alive. He was not really happy with it, even though he was one of the important pioneers of quantum mechanics. Anyway, let's now come to the heresy. The heresy is really taking a totally different approach. Einstein, of course it started with Einstein. He was really the leading figure who was not satisfied, fully satisfied. He said quantum mechanics works, but something is missing. He didn't like the indeterminism, and the famous word he used, God, he does not believe that God plays dice with the world. But more important was, he thought that quantum mechanics was somehow missing a description of the real world out there. He believed very strongly that there should be an objective world independent of observation and all that, with real properties. And he thought that quantum mechanics does not really describe that. So he had a long-lasting debate with Bohr. It really went over decades, and they were exchanging letters, and they were meeting at conferences, they had having long discussions and so on, always in a friendly way. They did not agree, but most people thought that, most physicists, let's say, at least believed that Bohr won the debate in the end. But we'll come back to Einstein nevertheless. And it was not the end of the heretic point of view. So the heretics, there were more. They were pushing ahead. Well, they were introducing something that's called hidden variables. That means that below the quantum world, all these people think there should be another world which is more like the classical world of the solar system. That started with Louis de Broglie, one of the earliest pioneers of quantum mechanics. David Bohm worked out a detailed theory based on the ideas of de Broglie. And even recently, the Nobel Prize winner of '99, Gerhard Toft, he's now moved into that camp of the heretics. He thinks, and he made that very clear in an interview, that all the strange phenomena, which I will describe in a moment, the strange phenomena associated with quantum mechanics can be understood by some kind of super conspiracy. I mean, something was determined at the beginning of the world, at the Big Bang. Things were set up in an extremely clever way to produce all these strange quantum phenomena now. But everything is really evolving deterministically. I put Calvinism here in parentheses because it corresponds to a certain extent to the Calvinist point of view, that God determined everything beforehand. It's extreme. But the general idea of these people is simply that quantum mechanics is something that's emergent from an underlying deterministic world. Only if we look at it a little bit less closely, if we ignore some details of the underlying world, then we get this quantum mechanics with this indeterminacy and all that stuff. So there has been some criticism of these concrete versions, for instance, David Bohm's of 1954. It is to a certain extent does reproduce quantum mechanics, but not in all respects. And anyway, for instance, David Bohm, he says particles do have positions and velocities at all times. This is very heretic. But if you look at it, these trajectories, these, trajectories means how they move, these particles, is very bizarre. So Einstein comes back, actually in 1935. He thought he really could point out now, for good, what was wrong or what was missing with quantum mechanics. This picture may be very confusing, and I'll only say a few words about it. He thought about an atom that's emitting 2 photons at the same time, photons, particles of light. And quantum mechanics predicts if you look at one of them and you measure a certain property of it, that automatically determines that's corresponding property of the other one, no matter how far away it is. And he called it a spooky action at a distance. He said that's absurd. It couldn't be. Something is missing. So it's roughly, if photon number 1 says yes, number 2 has to say no, and vice versa. In Schrödinger's language, one says, and that's a very common word now for that, the 2 photons are entangled. They remember that they have a common origin, no matter how far they are away. And that's a very, Schrödinger wrote it in German, actually. He called it verschränkt, strange word. We talk about entanglement. Entanglement of parts of a system that are not really separate. They remember the common origin. And that's one of the essential, crucial properties of quantum mechanics as compared to classical mechanics. Now, Einstein, Podolsky, and Rosen, they wrote this up in 1935 as a thought experiment, and it led to many debates and so on. Again, Bohr came in, and he argued that it wasn't a spooky action at a distance. And if you look at it closely, it is really something else. It really expresses some strange correlations. But we should remember that quantum theory says parts of a whole do not have individual properties which we may assign to the whole. The parts, they still remember that they're parts of a whole and therefore cannot conceptually be separated completely. Now, in 1964, there was an important step. John Bell, he proved, assuming, Einstein, Podolsky, and Rosen, they made certain assumptions about the real world out there, which had to have properties and shouldn't act spookily at a distance. Using these assumptions, he proved certain inequalities, certain bounds, certain correlations couldn't be larger than 2, let's say. And this was actually realized in experiments, starting with Alain Aspect. Since then, there have been many such experiments. He actually realized, in essence, the thought experiment of Einstein, Podolsky, and Rosen. And he found that these bounds, certain correlations couldn't be larger than 2. They actually were much larger. They were close to 2 times square root of 2, which is what? Which is almost 3. And that, in some sense, put an end to Einstein's dream. Einstein's dream of this reality in a very classical sense cannot be realized. So now you may ask, why are people like Gerhard still following? Well, they know all that, but they have to really, they have to promote this conspiracy theory that everything was determined from the very beginning. Okay, now, here, cosmology. Modern cosmology has another problem with the orthodox view. And what is the problem? Well, it was mentioned already. Where's the observer? If the whole universe is a quantum system, and modern cosmology treats the universe as a quantum system. And actually, modern cosmology says if you look at the sky, you see stars, maybe you see even galaxies, if you have a good telescope. You see these structures that are really frozen quantum fluctuations. These are facts that are generated in some way from a quantum state. But where would you put the Heisenberg cut between the classical and the quantum world? How does that happen? Where's the observer? Well, also, at least I would like to believe that events happen even without anybody looking. For instance, I think if I have a detector and a radioactive isotope and this detector clicks, I think it clicks even if I am not in the room, if I don't hear it. So that opened a new kind of debate. To this dilemma, one solution is the so-called many worlds interpretation. And that really says that every potentiality, every possibility that's contained in a quantum state, they're all real, they all happen, but they happen in different universes. So the universe splits continuously, almost. It splits into different parallel worlds in which different possibilities are realized. And what can happen does happen in one of the worlds. This is a very popular view with cosmologists nowadays, even though it seems at first sight a little bit strange, maybe. And an obvious criticism goes back to this medieval philosopher, William of Ockham, who actually is a compatriot of mine in some sense, because he lived in Munich and died there. Solution number 2 is that there is something that spontaneously creates facts. No observer needed, but it's happening. So that's a theory that was proposed by these 3 people. And then a somewhat different version of it is due to Rudolf Haag. Now, this is a 92-year-old physicist living in Germany, and I had the privilege of talking to him a bit in the last few years. He's really he's on the one hand a follower of the orthodoxy. He knew Bohr, he discussed with him. On the other hand, he thinks we have to introduce something which he calls a principle of random realization. And he, in particular, puts events as an ontological basis of the world. What does that mean? It's not particles, tables, things like that, which are the primal stuff of the world. It's events. And I said an event is something that's a fact that cannot be changed, which is localized in space and time. And he even has an idea how one could experimentally determine how large these space-time regions are in which these facts are being created. Then, going one step further, but this is now not worked out, this is speculation, one step further is that space and time should really be constructed out of these events. And certainly you can think of a particle as something that's really some consecutive events that are causally related. That you don't really see a particle, you see several events which you relate in time and in space, and it makes you think of a particle. That's his view, and I think it's a very worthwhile point of view. So, I'm coming to the end, and okay, I wrote 3 points to take home. The first one is that quantum theory is weird and is counterintuitive. Well, the 2 weird properties are these superpositions of states, which are both dead and alive. And the other thing is the so-called entanglement, that parts do not remember where they came from and don't have really individual properties. The second point is that quantum theory is indispensable, obviously. I mean, it's the best theory we have. I said that in the beginning. And the weirdness in particular even leads to these ideas of constructing quantum computers, for instance, that's based essentially on the superposition, strange superposition. So a quantum computer could do many things at the same time. The third point is something I did not talk about, I did talk that the battle continues, but I did not tell you that most working physicists actually do not pay any attention to it. You may think that's bad, but it just expresses the strength of quantum theory. It works no matter which interpretation you favor. As long as you're practical physicist, you don't have to worry about it. But it's very interesting for philosophy, and that's why I think it's a worthwhile battle to engage in. Thank you.
So, Werner, by the way, I just heard Leonard come on stage. So I heard this, I was asking a physicist to explain entanglement to me.
Yeah.
in a metaphor. And he said Einstein turned in his grave and Niels Bohr turned the other way simultaneously.
Yes, that's
at the
very
same
good.
time. Huh?
Very good.
I have one question. If entanglement occurs in space, does it also occur in time? You want to come up, Stuart?
I want to ask him about Penrose's interpretation.
Which interpretation?
Penrose. Let me first finish the question I had, then you go ahead.
Yeah, okay.
So
I don't have much to say about it. I have not studied that, and I will not comment on it.
You're missing the point.
No, he says he hasn't
Well, maybe,
studied.
no, I'm missing the point, so, but then maybe you should explain it. Okay.
So if quantum entanglement occurs across space, does it also occur across time?
That's true. If, let me talk about two particles. If they are in an entangled state, they will remain there until something happens, an event. That will break the entanglement.
So when I look at a distant galaxy in the past, am I creating the collapse now?
Okay. According to one of the interpretations, I think that would be true. I find that hard to accept, personally.
Chris, you had a point the other day where we were communicating by email, and you said if Schrodinger's equation evolves the way it does, nothing can be random. Could you comment because he spoke about randomness?
Well, I'll make one comment there. I mean, the technical way to put the comment is that the notion of decoherence doesn't work unless one assumes the environment is random. And that, of course, is a classical assumption. So in thinking of anything as classically random in quantum theory, we're actually building classical theory in. And hence we can expect to have a train wreck. But I also wanted to make a comment about the EPR experiment and the description of the EPR experiment as two particles traveling apart from each other and being interacted with separately. If the quantum state of the two particles is entangled, then as you defined it, there's no such thing as properties of the individual particles. So one doesn't have one particle hitting me and one particle hitting you. Rather, one has two particles together hitting both of us. And so there's no mystery about manipulating particles at a distance because the particles themselves aren't separated. Their state is completely overlapped across the entire distance that we assign them as having traveled. And the particles themselves don't experience that distance in any way. They're not measuring distance. So for them, distance in a sense doesn't exist.
This is what Einstein found spooky, but okay, it has been confirmed by experiment. So I agree.
Leonard and then Menas.
Comment on EPR or
just anything
in general? Well, Erhard, I'd like you to talk a little bit to connect the interpretations that you talked about with what was talked about earlier and the role of the mind and whether you need you talked a little bit about, but whether you need a physicist or somebody to observe something and what some of the pioneers thought about that issue.
Well, I mean, the pioneers, I think as Henry Stapp pointed out, it really goes back to John von Neumann, which I didn't mention in my overview. Very important. He was the first person to give a detailed, coherent, and mathematical description of quantum mechanics, and I think he was apparently the first one who thought that the mind was important. And then, of course, Eugene Wigner, he pushed it to the extreme that his own mind was important, not the mind of his friend. That would make it a rather subjective enterprise, all of quantum mechanics. So I find that hard to accept from my
Which interpretation do you favor?
Good question. Because that depends on when you ask me, the time of the day.
Or
No,
whether
I
I'm
mean,
listening. Huh?
I'm certainly favoring this minimalistic ensemble interpretation, as I called it. There's nothing wrong with it. But, you know, I'm a working physicist. If I apply physics, then I use that in my mind, and I don't worry about anything else. I said that's sort of the intersection of all the interpretations. But when I think about it, I think I sympathize, for instance, with Rudolf Haag, who thinks there should be something missing. There should be, you know, it's more or less what Einstein felt. Something is missing, but it cannot be realized the way Einstein thought, because we have these Aspe and other experiments. But there is something missing which we should learn to understand, how facts are actually created. This is not an interpretation, but this is what I think.
I do have a problem here, because what I want to ask is a mind-independent universe even empirically possible? I mean, it's a metaphysical idea. A mind-independent universe, to me, is a metaphysical idea, because there's the moment you need an observation, in any case, right? That's not science.
Yeah, okay, that's more or less the standard view, standard orthodox view. So I'm deviating from that in a certain extent. But that goes a little bit in the direction of Einstein, because I think, at least as physicists, we have to work as if there is a world out there which exists independent of us. I am not saying it does. We cannot know that. But
that's an idea. It's not a scientific fact.
No, it's an idea. It's not a scientific fact. But we are talking about interpretations. And
yes.
Len was asking me what I favor. I'm tending in that direction.
Mena's last word.
Erhard, thank you so much. In terms of, you brought up the issue of cosmology. So here
Yes.
is an issue, a big issue with cosmology, between the distinction or the problems between cosmology and the standard model that you mentioned. Cosmology today, we know the cosmological constant is about 120 orders of magnitude smaller than the standard model predicts. This is really a massive failure of either one of them or both of them. Could you comment on that? Where are we going in terms of trying to bring together general relativity and quantum theory?
Well, this is certainly one of the big mysteries, this extremely tiny value of the cosmological constant. I mean, we have not explained what it is, but it's something that seems to be true about our universe. It's a big mystery. Now, I don't quite agree that the standard model predicts this and that, because that's not so clear in quantum field theory. This is a rather simplistic computation that gives you this 120 orders of magnitude. Or with supersymmetry, it's only 60 orders of magnitude. But it's somewhat simplistic, because it's talking about zero-point energies and cutting it off rather arbitrarily. Still, I think there's a very tiny constant that needs to be understood. And of course, one way to understand this is something that's rather popular. It's the multiverse. And I mentioned the many worlds interpretation. That's one form of multiverse. That means, you know, there are many worlds out there, and only few of them are habitable. And only the ones...
Well, the idea being that there's many worlds out there with essentially different laws, and they all exist in some sense. And of course, we would exist in one that has laws that allow us to exist. Obviously, we couldn't exist in any other. So what seemed to be a coincidence, if you just observe your own universe and go, why are the laws so finely tuned that they allow us to exist? That becomes less of a mystery if you think, oh, well, there's many universes, but of course we exist in one that allows us to exist. But I have to say one other thing about the multiverse, especially before you say anything, Deepak.
No, but
which is that the multiverse is a consequence of some physical theories, not something that physicists conjured up to explain the mystery of the fine-tuning.
Yes,
Right.
I agree. So for those of you who are not physicists, the bottom line is it works, quantum mechanics, but we have no idea what the heck is going on. Okay, I'd like to.
We're happy that there are still
Right.
mysteries to
Yeah.
solve because that's what's
Absolutely, absolutely. I was just going to conclude with Arthur Eddington, who said something unknown is doing we don't know what.
But it all deserves very careful study,
Yes,
which is why you're all here.
stay tuned. Thank you, sir.
Thank you.
Thanks.
Quantum state is something totally different. A quantum state is often called the wave function, denoted by this nice letter, psi. It doesn't describe facts, like something is sitting somewhere and moving at a certain speed. It does describe possibilities and the probabilities for certain possibilities to be realized. In particular, particles do not have precise locations or velocities. It is not a deterministic theory. That means the future is not fully determined by the past. The present does not determine the future, and there's a fundamental difference between past and future. The past consists of facts, documents, records, things that can be read about the past, history. It's there. It cannot be changed. The future consists of possibilities. There's a very strong difference and asymmetry between past and future. So the basic problem, to come to that, and that's the problem about which the whole debate or battle of the interpretation rages. The basic problem is, how are facts created? From this wave. I will talk about something that was talked about before already, namely the interpretation of quantum theory. Now, before there were basically 2 points of view that were being promoted. I'm trying to give a little bit of an overview and maybe put it into context to a certain extent. Let's briefly talk about quantum theory, why we bothered talking about it, and what it is. I'll give you some rough idea. So it's certainly the most successful theory in the history of physics. That's what I want to say, and that was mentioned already. It's precise to 10 decimals, or maybe 11 now. It covers everything from subnuclear particles, atoms, molecules, everyday objects, stars, galaxies, and the universe. It explains lots of things, the stability of atoms, the stability of tables, and also the stability of the genome, something that was stressed by Schrödinger. We'll come back to him. It forms the basis of modern microelectronics, in particular cell phones, computers. All our modern technology would not exist without quantum mechanics. So, what is it? Before quantum theory, I call it quantum theory, it's a little more general. Before quantum theory, there was the classical theory of physics, and a typical example, the example, was really the mechanics of the heavens. So this is supposed to be the solar system, supposed to give you some rough idea of the solar system. And this solar system was understood by Isaac Newton, and it was like a clockwork. It was called Newton's clock because it has the feature, if you know the present state of the solar system, that means if you know where every body here, every planet is at the moment, and its velocity. If you know those data, you can predict everything in the future. And equally well, you can predict the past, because the past is really like the future. In the classical theory, there's no difference, really. It's a very mechanical worldview, and it has been superseded by quantum theory. Now, the state, I said the classical state is just all objects, you know where they are, and you know in which direction, how fast they move. The interpretation into two groups. There's the orthodoxy and the heresy. And the leading figures of the orthodoxy, of the orthodox camp, was certainly Niels Bohr, and then many people after him. I'll come to that. And interestingly, the heretic camp that said this quantum theory was not complete, there was something essential missing, was led by Albert Einstein, 2 Nobel Prize winners in 2 consecutive years. So that tells you already that's not so obvious. I mean, if the most famous physicist of the 20th century belonged to the heretic camp, and he was not only the most famous physicist, he was also one of the most important pioneers of quantum theory. But he didn't believe the orthodoxy. He wasn't happy with it. But let's first talk about the orthodoxy. The first crucial thing, and that's an insight that is not denied by anybody, it's the so-called ensemble interpretation. What does that mean? It means that the quantum state does not really refer to an individual object or system, but it describes an ensemble, a collection of identically prepared systems. And it really contains all the function quantum state that describes only possibilities, potentialities. Well, it's understood to a good extent that certainly the interaction with the environment is the essential point. So one example which everybody may know, if you have some radioactive substance, you know, a radioactive atom decays and you have some kind of counter, some detector as it's called, it will click. So that means there's a certain fact created in a certain place and at a certain time. This we would like to call events. The event, to say it again, the event means just creation of a fact at a certain place at a certain time. It's not a point, but it's localized in space and time. So the point of quantum theory is that the events are not really predictable, only their probabilities. The probabilities that certain facts are being created. So far, I think there's consensus. The consensus goes away when we ask, is this all we can say? So, now let's go back to the history and the main battle line. There's an orthodox camp. If I roughly group